Welcome everyone to this webinar. My name is Iva Verdnik. I am the product manager for the MD line. So today we're going to talk about our new current clamps. Give me a moment to share my screen. All right, so this is the MD9273 Bluetooth current clamp with power functions. We're going to talk about its applications and its uses. This presentation will go through the features of MD9273. We're going to touch upon some differences and similarities from the MD9272, which was the predecessor of this clamp. We're going to go through general locations where they both can be used, and I'm going to present you a number of practical examples. So while you will find that the MD9272 and 73 are quite similar, you will also find that the new clamp, the 73, has a number of new applications. Let us start with the introduction and the features. MD9273 contains a unique combination of features that cannot be found in any other clamp on the market, and that makes it the superior troubleshooting tool. So the biggest news, the biggest feature that came new with this clamp is the ability to connect to Metrel testers over Bluetooth. The supported models are MI3155, MI3152, and MI3325. Whenever I say Metrel testers within this presentation, these are the three that I mean, so to make everything easier. Other testers with our new operating system and color screen are going to get supported eventually. The measurements that are done using MD9273 as an adapter to the main instrument over Bluetooth connection are called the online measurements. And most of the measurements that are supported in the current clamp are also supported to be done online. So what are these supported measurements in the MD9273? Already the name mentions the leakage current ability. So we can reliably measure currents from about 10 microamperes upwards. While measuring low currents in about milliamp range, the current can sense the losses in the system, and it can predict the source of those losses. So are we talking about nonlinear loads, about the insulation losses, or the combination of the two? The clamp jaw is shielded, and therefore it's very resistant to environmental disruptions. Then we have the basics of power quality. The clamp can measure active, reactive, and apparent power. It can measure the power factor and the angle between current and voltage. The harmonics. The clamp can measure both current and voltage harmonics up to the 19th, and it can also measure the total harmonic distortion in both the current and voltage. We have the inrush current recorder. The inrush current can be measured as just the maximum value using only the clamps. But when we connect them to the Metrel tester, it can record a graph. The recorder sets up and it creates a graph, and it also saves the table with the data. This recording can be saved into the structure element in memory organizer and then transferred into the software as well. The VFD filter allows for easy troubleshooting of a type of motor controller. And then we have the 120 Hertz notch filter, which is a very special function of this clamp. and it enables us to search for installation breaks while the installation is operative. Finally, we have the basic multimeter abilities. We can measure voltage in TRMS, AC, or in DC. We have the secondary measurement of frequency. We have the AC current up to 100 amps. And we have the basic recorders of minimum value, maximum value. We can hold the value. There is the peak function for catching fast signals. And finally, we can measure the crest factor, which can tell you more about the type of signal and its difference from the ideal sign. The overview of the applications and in general locations where in both MD9273 and the earlier 72 can be used. So the clamps are mainly meant for work in installations in low voltage range. And here we have the full selection. They can work in basically any installation in this range. We're talking about home, office, industry, medical, agriculture, pretty much anything. Leakage current measurements can be used to troubleshoot RCDs. They can be used to troubleshoot the installation and the functionality of installations. And then we have machines and motors. They're mainly industrial, used in industrial applications. And in there, fast troubleshooting is particularly important to save the money to the company. The combination of leakage current and power measurements is extremely useful in medical locations, where the installation tends to be the main safety mechanism. Then we have electric cars. They often use the transformed DC back to AC to actually do work, and also charging is often done in AC. So these are the parts of the electric car that our clamp can be used in. And since it is such a small clamp, it is very useful in those tight places under the hood. Then we have portable equipment. It needs to be tested for safety measures, and it needs to be tested for functionality or troubleshooted just as much as larger machines need to be. And MD9273 is the great tool for them. If we talk about the audience for MD9273, the clamps are primarily targeted at people who already own one of the supported Metrel testers. We're talking about people doing installations, people doing the inspections of installations or devices, and people doing maintenance. Now, let us start with the details about the clamp's abilities and the applications. Now, leakage current is normal part of operation in more or less any installation or device. Everything leaks slightly. Either the installation is not perfect, there can be some induction from adjacent wires. These are the types of reasons that there is always some leakage present. The installations or systems need to be designed with this leakage in mind. We're talking about sizing of the wires or RCD selection. And there are other similar considerations that must be taken into account. The normal level, the everyday level of leakage current is very rarely dangerous. Perhaps the only occurrence where this can happen is if installation that was not designed for moist or wet environments suddenly gets wet. However, if leakage current becomes different from this basic expected level, then it can be taken as a symptom of problems. It can be symptom of installation break, unintended contact, a failed connection of accessible part, failed connection between line and neutral, functional fault, and similar problems. The source of this fault can be anywhere. It can be in installation, in machine, or in portable appliance. Even during failure, usually the leakage current does not leave the range of milliamps, but it can still raise to dangerous values. Other problems that it can cause in installations, if it gets too high, are RCD stripping, overheating in parts of installation, energy losses, high contact voltage on accessible parts, and other similar issues. Now, it has to be mentioned that all leakage current measurements are supported by the MD9272 as well, so with the old clamp. If we're talking about the locations and ways of measurements, we're talking about mainly looking at distribution boards, sockets, device connections to the installation. Now let's look at the actual measurement methods. We're going to use this simplified schematic of a bus bar in a distribution board. So here at the bottom, we have the main supply connections, and on top, we have connections to different parts of the installation. Now, leakage current, as it flows away from its designated path, generally ends up somewhere in the protective earth wire. So the easiest way to measure it is simply to use the clamp to measure it, how it flows in the protective earth wire. This method is called the PE or the direct method. However, this method has a mild disadvantage. Some current is going to leak away from the part of the installation where we are trying to measure and only end up in the collector PE wire. So when we are looking for the location where our leakage happened, we may not find it. Usually, if this disadvantage turns up, we have an installation that does not have very well insulated walls or floors. However, most installations are isolated enough that this does not happen. This is not such a big problem. However, if it turns out to be, if we cannot find the location of our leakage using the PE wires, we have the second method available. This is the differential method, where we clamp the line and neutral wires together. The difference between them is the leakage current, and this method takes into account the whole difference, so even the current that might have run away from the local protective earth wire. However, this method has a mild disadvantage. In this case, we are looking at a very small difference between two relatively large currents that are normally flowing in the line and the neutral wires. So the clamps must be particularly well shielded and a well executed measurement instrument to be able to reliably sense this difference. The MD9273 is absolutely up to this task. Now, both of these measuring methods can be connected with the clamp's basic recording abilities. So we're talking about recording the max values to find any slowly rising peaks of leakage current, while the peak value is less precisely measured, but it can catch very short peaks down to about 25 microseconds. So here we have our first example of using leakage current measurements for troubleshooting. This is a medical location. Typically, the surgery room is going to have IT grounding system, which means that it is isolated from the common ground of the hospital. This allows the system within the surgery to have higher availability. In case of an installation break, the system is going to remain safe and functional, but it will typically start functioning like a TN grounding. In hospital settings, where the patient safety is of utmost priority, there are often additional RCDs to ensure safety in case of a second failure. Now, the main Metrel instrument to be used in this environment is the MI3110. However, the MI3110 will only test the safety measures for us, but it cannot point to the source of any problem that it discovers. So this is where our MD9273 will come in handy. The medical devices generally come with external PE wire, so separate PE wire from the supply wire, which makes it particularly easy to use the direct method of measuring leakage current to locate our problem. Let us look at the video of this application. The video is shot in one of the Slovenian hospitals. The surgery room is equipped with multiple devices which are stacked into a tower, and all of them have external PE wires. In the background, we can see the installation monitoring device at one point. I will point it out. And the monitoring device has started the alarm. Now, we have to find which of our devices is the source of the leak, and we do that by simply clamping each of the PE wires until we find the source of the leakage. So here in the background, we have the installation monitoring device. I wanted to show you this schematic, this diagram of the problem that I just described. So we have an installation failure in line 1 that causes a high leakage towards the PE wire. So here, this is our source of the problem. And it shows this diagram also shows how this breaks the isolation of the system. So now both the general earthing of the wider system and the isolated part of the earthing are connected, and the whole system works as a TN, a grounding system. Now, in IT systems, the limit for installation is usually relatively low, and this enables us to work with the leakage clamp where it is the most precise in the milliamp range. Our next application, we can check functionality of heaters in a machine using differential method. So in this case, we have the supply wires of the machine very easily accessible, which makes the differential method ideal for use in this case. Again, we can use the max function to record the highest leakage of the heaters in the machine, or we can use the harmonics function to filter to only the supply frequency. The machine I'm going to show you is actually one of the machines we have in Metrel production hall. The working within it is relatively dangerous. We are close to the heater and we are close to the electrical installation. So I need to use the protective measures for both of these dangers. The supply wire, in this case, as I mentioned, is very easy to recognize, and this makes the differential method so ideal for this case. And I'm going to use filtering to the first harmonic to only watch how the supply frequency is leaking. And I'm going to use recording to the maximum value so that I know which is the highest peak of the leakage current that is happening. This measurement is part of regular maintenance, and we are basically checking how much the heater is leaking during normal operation or in different operation modes. Our next application is essentially the same thing that I showed you in the schematic form earlier. So we are looking at we are looking for the part of installation that is leaking using the connections of protective earth to the common bus bar. So it is possible to clamp multiple wires at the same time, which will help us work faster. And once we see leakage in a group, then we can go look at the details. We can go look at each wire separately to finally find our source of the leakage current. So the next ability of the clamps that can be very well used in troubleshooting are the power measurements. So the power consumption, power use is one of the very essential functional tests for devices or parts of installations. Power within the specification usually means that there are no issues that need resolving. However, changes in either power consumption or power variables can be very indicative of a type of malfunction happening. So power factor can indicate the type of problematic device or the part of the device. So if we have trouble with capacitive devices, or even if we have capacitor banks present in the installation, it can cause a very distinct drop in power factor. However, if we lose some inductive loads to malfunction, it can change the power factor in the other direction, so increase it. Sudden imbalance between phases in a three-phase system can indicate a problem on one of the phases, some malfunction, which will cause the other two phases to draw more power. Then we can look at power losses caused by leakage current. So even particularly if we have inductive leakage, this can cause quite high power losses. Higher consumption can also indicate problems like problems with connections or weakened connections, some aging equipment with lower efficiency, and similar. If we find lower consumption in parts of the installation, it tends to point to a whole device failing so that it doesn't draw any power any longer. This is just the connection required to do the power measurement. We connect the power leads using the clamps or using the probes, and we connect the clamp to the phase line so that we have both voltage and current measurement. Here we can use the alligator clips or the optional magnetic clips for easy attachment. So let's see how this measurement is done. This is again an industrial distribution board. So I'm going to use the probes and clamps to connect to the neutral or to the PE. And I will be using the clamps and the other probe to measure power on each phase. The measurement should be done on all three phases so that we can compare results on them and look for any imbalance in them. Again, different functions of the clamp can be used to narrow down our result and to look for other problems, for possible other problems. So, some examples. As I already mentioned in the video, we look for imbalance or a power draw between the three phases in distribution board. The imbalance can be a very serious problem in the installation if it reaches more than about 2%. Then we can use power measurements when looking at three-phase machines. So we need to test the functionality of each of the phases to troubleshoot the machine's ability to work. Then the third thing that we can look at, we test the power draw of an appliance. So now we're testing the supply to the appliance, and we are looking at different work states or operation modes of this appliance to check that all of them are working as expected. So that we test for correct functionality of a device. We have the THD and harmonics measurements available in this clamp. So we're going to first look at a little bit of theory behind them, and then we're going to go ahead with the applications for troubleshooting. The harmonics are a mathematical way of describing signal shapes as sum of signals at different frequencies. The frequencies that are summarized, that are used in harmonics, are the base frequency and its integer multiples. So, for example, in installation, we have the base frequency of 50 Hertz or 60 Hertz. The second harmonic is going to be at 100 or 120 Hertz. The third at 150 or 180, and so on. The signals that contain a non-negligible amount of harmonic content usually indicate presence of nonlinear loads in the system. So while we have no ideally linear devices in reality, usually harmonics only need to be considered in systems where we have semiconductor solutions present, where we have magnetic devices that work in saturation or otherwise outside the linear part of the characteristic, where we have arc equipment, for example, welding equipment, and similar nonlinear devices. The system needs to be designed to work with the expected harmonic content. So similarly to leakage currents, also harmonics are part of the design considerations for systems. But harmonics can be a very big problem. So where it is necessary, some filtering solutions are added to the installation to lower their presence. As a troubleshooting device, the harmonic content is very typical for each type of nonlinear device. So, for example, semiconductor solutions or transistors tend to add the third harmonic into the signal. Then we have square waves, which are used as control schemes. They tend to have very high harmonic content at odd harmonic numbers. We have then the total harmonic distortion, which is a slightly convoluted way of adding the harmonic sizes into a measure of power stress in the system that is caused only by the harmonic content, and it can be used as a measure of how different our viewed signal is from the ideal sign. These are all very typical harmonic signatures, and we are looking for any differences from the expected harmonic content, and we can use these changes in troubleshooting. Both MD9273 and MD9272 can measure up to the 19th harmonic for both current and voltage. The actual measurement is done by using the clamp jaw or the test leads to connect the instrument in the same way as for basic current or voltage measurement. So some examples of using the harmonics and THD for troubleshooting. Filtering to the first harmonic will show the linear effects in the installation. So this will exclude all effects of higher frequency content, and it removes any distortion. So leakage in the first harmonic will show us linear faults like phase to ground contact, broken insulation, trouble with heaters, and similar issues. Now, if we find the unusual third harmonic, unexpected third harmonic, it can indicate problems with power generators or other active loads. In case of power generators, it has to be stressed that the third harmonic usually does not mean magnetic problems, but some other type. I already also mentioned that a high third harmonic can be part of normal operation of a system in case it is designed for it. High fifth harmonic or unexpected fifth harmonic can be indicative of problems with vibration in motors. So usually these are mechanical problems. Either the motor is not fitted well into its enclosure, or there are mechanical problems between the rotor and the stator. And this can show in the electrical system as high fifth harmonic. Unexpectedly high THD can indicate the saturation of an electric machine, but it has to be mentioned that in systems with high presence of semiconductor solutions or consumers, the THD can be very high by default. Then we have higher harmonics if they happen unexpectedly. They can mean that we have some semiconductors that are clipping, so we have unexpected square waves in the system, or they can mean problems with some very specialized equipment. Our next ability that we're going to present is inrush current recording. So inrush current is a very short and very high peak of current during the startup of electrical machines that lower into operational value within a very short time. Its size tends to be tens of times the nominal value, and it happens both in case of inductive loads due to startup magnetic effects, and in case of capacitive loads as the capacitors charge. We are talking about maybe 40 or 50 times the nominal value, but it only lasts a couple of milli or even a couple of microseconds. The inductive and the capacitive effects can compound each other, and so we get like a really, really high peak of current. Obviously, there needs to be some system in place to limit it. Otherwise, the whole circuit would have to be oversized to accommodate such a high startup current. So the measurement of inrush current will tell us about the health of the machine that we're measuring and about the health of its inrush limiting circuit. So the MD9273 contains a recorder for inrush current. However, to use the full potential of this recorder, it is necessary to use the connection to one of the supported Metrel testers. This way, it is possible to use the current or voltage value trigger. We can set it up as any parameter in the instrument, and we can show the recorded data in graph form. Now, this graph, again, is very typical for each type of the machine, and we can use it to diagnose problems with it. So let's look at the video of how to measure the inrush current. We have a motor here and easily accessible supply wires. So we set up our clamp to measure the current. We set up the instrument again with the trigger and so that it waits for the trigger value. And here we can see how the graph is shown. Now the graph is going to show us the recording about 1 second before the threshold was passed, while the length of the graph, so how long after the threshold is measured, can be set up. Our next ability is the variable frequency drive. So a variable frequency drive, or VFD, is a type of a control scheme or a way of controlling a rotation in three-phase motors. It uses pulses at different frequencies, and these pulses achieve a dual objective of providing a certain frequency and a certain effective voltage value to the motor, which enables it to control the rotation, the speed of rotation of the motor. It comes with significant power saves compared to other ways of controlling the machines. Now, these pulses, as I mentioned already earlier, have very high harmonic content. They reach very high frequencies, and a specific low-pass filter is required to observe their frequency and their voltage, their effective voltage effectively. Now, the relevant part of the signal is usually close to the first harmonic, somewhere in 30 to 60 Hertz range. But the VFD filter is usually set up a bit higher to accommodate any outliers. So VFD filter is a low-pass filter that will show us only the relevant part of this modulated pulsed signal. This application will be found in industrial application motors, and it is ever more common in electric cars. So let's look at the execution of the measurement. Here we are using the optional Metrel lines and probes and alligator clips at the end. We set up voltage measurement, we set up the VFD filter, and we start the motor. What we are looking at here we are checking that the integrated display of the controller, of the VFD controller, is showing us the same values as we measured with the clamp. In case there is any difference between these values, we know that we have a problem. We can also listen to the motor, how it starts up and how its rotation changes with both voltage and frequency values. So now we have come to the 120 Hz notch filter function. Now, this is a unique function that is not found in any other clamp or combination of clamp and instrument in the market. As we're going to take a look, it will enable us to look for installation problems while our installation is in operation. Now, if we look at the what notch filter means and how it works. So a notch filter is a filter that only lets through a very narrow band of frequencies or even only a single frequency. In our case, the 120 Hz is the frequency that Metrel testers use when they use it to for the two-clamp method of earth resistance measurement. And this frequency was selected because it is relatively far away from either any supply frequencies or from their harmonics, so it can be easily discerned how it travels around the system. Now, generating signals into the ground system can have multiple uses. As I mentioned earlier, our testers use it in two-clamp method, and they use it to measure the resistance of the grounding system. However, the signal travels throughout the whole system, and now that we have a remote clamp, we can use this combination of generator and the clamp to look at the problems in other places in the system. So the main application deals with locating the installation failure in installation. The signal is injected into the main grounding wire, and if there are no problems, it just flows into the ground. However, if there is an installation failure in the installation, the signal will be pulled into the local protective earth connection and returned by one of the other lines. So it is possible to track where this circuit is connected so that the signal can return. The application works much better in TNS grounding system, where the impedance of grounding system is very low, which leads us to very low noise and to high generated signal. Now, to look at the diagram of the problem that I described earlier. So we are generating the signal into the common protective earth wire, and here in the drawing only has one consumer, but there can be multiple in the system, but only where there is installation problem, the signal is going to have a return path so that we can find it when we clamp the PE wire, that the signal is flowing into this consumer, and we know that we have found our installation fault. So here is the video of how this is done. So again, we have an industrial distribution board. We use the generator clamp 81019 to generate the signal into the main protective earth wire. So we just set up the protective earth, the two clamp method on the instrument, and then we use the clamp with the 120 Hertz filter activated. And now we look where this signal is flowing. Again, like with the leakage current measurements, we can firstly clamp multiple wires to look where our signal is flowing. And only when we find it, we can go take a look at each wire separately. So this enables us to work faster. Once we find where the signal has gone, we know which part of the installation has the installation problem. Another thing that has to be mentioned, while we do need both the instrument and the clamp for execution of this method, they do not need to be connected over Bluetooth in this case. We only need to have them both, but separate. So the online measurements, I've been advertising them already at the beginning of this presentation. So almost all measurements that MD9273 supports can be done over the Bluetooth connection on one of our supported Metrel testers. The MD9273 is put into Bluetooth mode and therefore cannot be used during the measurements. Measurements are only accessible through the tester under the separate category clamp measurements, so they are easy to find, easy to separate from other measurements in the tester. And so all these measurements can be executed through the tester, and then their results can also be saved into the memory organizer. This enables the user to put the clamp into the measuring location and then stand well back while the measurements are executed. So they need less protective gear, and their work is easier and more comfortable. So how this is executed, the online measurements. Note that here I will only be using gloves when I put the clamp into its position. But while the measurements are executed, I can stand well back and don't need the gloves. The measurements are selected from the group current clamp, and the results are sent to the instrument from the clamp. When I'm happy with the results I measured, the results can be saved into the memory organizer. Now, once again, when I return for the clamp, I need to use protection again. The measurement done for this presentation is again the differential leakage current on the motor supply. Again, this measurement was selected because the supply wire is easily accessible, and the differential measurement can tell us a lot about the health of the motor. So we have come to the end of applications for MD9273 and also for its older brother 72. I thank you for your attention, and I'm returning then the word to Mojca.